And here we are, it's the physics video lecture. Physics 203, video lecture 27. I'm going to pick up where we left off, talking about the wave equation and the so-called Eikenall equation. And that chart or that table that I started last time, I'm going to complete, and then we'll see where that takes us. Okay, so just for some background, we're doing what's called geometrical acoustics. If this were electricity and magnetism, we'd be talking about geometrical optics, okay? But acoustics, because we're talking about sound waves, but of course we just had a wave equation. So there are going to be a lot of formal similarities. With the difference that our sound waves in a fluid are longitudinal as opposed to electromagnetic waves, which are typically transverse. Okay, be that as it may, so let's go ahead and start. We have a wave equation, d squared phi dt squared c squared del squared phi. And we're referring to the wave speed as c and not v because we have some velocities going on in fluid mechanics. Okay, so this is not the speed of light, it's just the wave speed in the medium. Okay, and as such, we know that c is actually a function of position, derivative of pressure with respect to density, or square root thereof. Okay, and what we did next was investigate traveling waves and traveling plane waves, and then we generalized. So we had phi is equal to a e to the I k dot r minus omega t for the plane wave. Then phi is equal to, and here a, omega were both constant, but then suppose we had a of r, okay, for that amplitude. Then it's not going to be that simple when we go into the wave equation, but what we did was we assumed that this changes very slowly, okay, and then we said e to the I c of r and t, where a of r changes very slowly so that we could treat it as a constant. It's possible to do what we're about to do fully rigorously, and then you do a couple of approximations later on and get to the same place. Okay, maybe we'll put that on the homework. So where a of r changes slowly, and then what we end up with is we expand c, we just say there's a constant plus gradient of c dotted into r plus d c dt times t. So we expand around some arbitrary point chosen. And when we compare this to k dot r minus omega t, minus omega t, so we compare this to this, we get this gradient c is the vector k, and deep c dt corresponds to minus omega, corresponds to minus omega. And that's how we get the Eikenall equation. So just to remind you, and the idea of this thing changing really slowly means that instead of just a plane wave, where k is pointing in that direction, we can gradually have k change. Okay, so this becomes a function of position instead of being a constant vector. Okay, so we set that up, and we obtain these following relations that I'm going to repeat for us. So I'll start that chart. This is going to be a full pager for sure. So we're going to have fluid mechanics on this side, and we're going to have point mechanics, point particle mechanics over here. So what we had with the fluids, I'll take what we had up there for starters. So we're starting with phi equals a e to the I c, as this stated. Yeah. So we had that, and now we have gradient of c is going to be our k. dc dt corresponds to our minus omega, and from kx squared plus ky squared plus kz squared equals omega squared over c squared, which was just the general relation between k and omega, we now obtain a differential equation, namely dc dx squared, and I'm writing it out. We could also just say gradient of c squared, which is what this is, expanded out, z squared omega squared over c squared, and of course this c is equal to a function of position, making the right side of this equation a function of position. Differential equation. This is that Eichenal equation. And we have that up there. Yeah, actually, we also have C is equal to C0 of R minus omega t under circumstances that I'll just bring up in a moment. Okay. Because omega is being treated as a constant. Equals constant. Okay, so good. What do we know about point mechanics? Point mechanics, we don't actually start with this thing here, but we do have, and I'm just going to line these up exactly, we have gradient S is equal to K, or I'm sorry, it's P, and then the S dt is equal to minus E or minus H, the Hamiltonian. And then here we have px squared plus py squared plus ez squared. When we solve for p squared, 2m e minus u. Okay, that's just from the Hamiltonian. You solve the Hamiltonian for p, this is what you get. Then when we take the gradient s equals vector p, we have ds dx squared partial s partial y is equal to 2m e minus u. And that's our Hamilton-Jacobi theory, our Hamilton-Jacobi equation under the assumption that the energy is constant, and then we know that we use S naught of R minus E times T. And so for a problem in point mechanics, we know that we can use the Hamilton-Jacobi method. I should, okay, no, I'll be on the next board. Okay. So this is where I ended up with last time. We have, excluding this thing here, which we'll come to later, we just have a perfect identification if we just change the names of our symbols. So this was a problem in fluids, geometrical acoustics. You can obviously just think of it as an optics type of problem. And we don't know how to solve this yet. We just learned about this at differential equation, but it turns out we already do know how to solve it because we have the Hamilton-Jacobi formalism. So we could even add, well, we'll get there later. So I'm just going to write here Hamilton-Jacobi formalism. So we ought to be able to apply that over here if we're careful. Okay. Okay, good. So this is the first half of what I want to put up. So we're going to split the board again. Let's see what else we can identify here. And actually, let's go ahead and add something to this. So down here is the short wavelength limit. Okay. So short wavelength limit is what we have down here. And that has to do with the fact that this thing changes very little. Okay. And short wavelength then corresponds to large K. So good, we have that. Now let's split the board, and I hope we can fit everything we want to do down here. Okay, so we're still talking about point mechanics here, and now we know that Hamiltonian mechanics, is what leads up to this. Okay, so we have to know Hamiltonian mechanics to apply this formalism. And so in Hamiltonian mechanics, we have P dot is equal to minus dH dr. R dot is equal to dH dP, taking all three derivatives at once. We're dealing with a single point particle on this one right here. Okay. And we also know that we have dH dt equals partial h with respect to time. And I should say out here as well, we're talking about conserved energy. I said it, didn't write it down. So if you want to write down energy is constant, that's when you're allowed to do this right here. Energy E, H, constant. Okay. So that's what we have if we're doing Hamiltonian mechanics. Now that must also be occurring over here. So if we just translate these, the P is like the K, so over here we must have K dot is equal to minus D omega D R, and R dot is equal to D omega dk. Vector, both of these, three derivatives. Okay. this we're seeing now, this is the group velocity. Group velocity, I mentioned that the other day. And we also must have v omega t equals partial omega with respect to time. Okay. We're going to be taking omega constant. Okay, so we have that much, so there's one more layer here, namely, where does Hamiltonian mechanics come from? These equations can be seen to come from a variational principle, which is what we started with. So the variational principle that'll hold true in this scenario, constant energy will be Maupertuis. Okay. So we have variational principles. M e minus u square root dl equals 0. So that's Maupertuis. Or we would be able to write it ds naught. It could just be p dot dl. Okay. Where P and DL are parallel, right? That's what this expression is, of course. You see it up there, right? P root 2 L dot DL. So that's another alternate formulation of this, and that was when we originally had that sum over the P dq that you'll remember when we were doing Maupertuis. I should write Maupertuis a little more clearly, okay. Maupertuis. Do I have a third formulation for this? Oh, that'll do. Okay, then what do we have corresponding to this on the wave side? This is, after all, the point mechanics side. This is originally the wave side. We have remember, this is the right side here, omega squared over c squared. So that's the object that's going to be in our equation. So here we have integral omega over c dl equals 0, or variation of k dot dl equals 0, or k and dl are parallel. And this, as we're going to see, is Fermat's principle. And yeah. So this is going to make, this is a, I'll check Fermat. So right here I'm going to remind us of Fermat first, and then there's a little confusion with the letter C, but we'll just deal with it. Okay. So Fermat, we have integral, you know, Fermat is the principle of least time. So maybe we would write T is equal to integral dl over V. So that's the principle of least time. And then you can say that that means the integral of n, and in this case, n is the index of refraction. Let's write it with variation. Variation integral n dl equal to 0. And then you write n is equal to, this is in optics though, so let's make a little note of that. So In optics, then we say that c is the speed of light and v is the wave speed in the material, right? And that wave speed is always less than or equal to the speed of light, therefore n is greater than or equal to 1, okay? And it's a function of position because the index of refraction, you know, it's a function of position, waves speed function. Okay, so when I use C and D, I'm using the letters a little bit differently. Over here, this is the wave speed in the medium, so that would be that one, but, so I'm just gonna write here optics. That is to say, this omega over C, where omega is a constant, C is dependent on position, that is our N, okay? That is our N dl. So again, under here, under the red line, that's optics, just to remind you of how Fermat's principle of least time. I'll write that out here as well, least time. Right, that's usually the first variational principle we ever hear of in optics. Okay, so yeah, we have all of these relations now. This is what we've studied all semester. Okay. Different formalisms. And we now have for waves in the short wavelength limit this formalism. We have all of this. We inherit all of this. And so Fermat's principle, we're going to name this N. Okay, maybe I'll use capital N. This is what we had on that midterm exam. N of R dl equals 0. So this is the one we're going to talk about. Okay. So this is Fermat's principle, and that's corresponding to Maupertuis' principle, okay, variational principle. And here, along in the direction of the momentum, and here we have to say integrated along a ray, the direction of a ray. So that's what I indicate with this parallel sign. Okay, so here's our plan. Let's see how we're doing time-wise. Fantastic. Okay. It's all up here on the board, and our plan now is to work the left side here, and what we want to do is prove Snell's law. That's going to be our big challenge and triumph when we use this formalism here to demonstrate Snell's law, which is the elementary optics application. And as you'll recall, we actually had this as a problem to demonstrate Snell's law. So what we're going to do, I'll write this down as homework, but I'm actually going to probably do the whole thing starting today and then next time as well. Yeah, let's set goal here. So I'll put this as a note. Next, show Snell's law in 2 ways. Okay, we want to prove Snell's law. One, using the variational principle. That was that bonus the other day. I'll show you that it's pretty basic. Variational principle, blue star. Okay. And 2, using the Hamilton-Jacobi formalism. Hamilton-Jacobi formalism on this thing over here. Okay, on the Eikenall equation. Double blue star. So yeah, it's great. We get we get to talk about acoustics, optics, and what have you, and we're reviewing our Hamilton-Jacobi theory, and we're even reviewing our variational principle. So. So we'll do the first one first, and then we'll tackle both of them, and I'll at least set them up. I'll set them up, you guys tackle them, and then I'll probably come back and do them after the break. Okay. So first, Snell's law. So since we know Snell's law, let's just sketch what we remember here. In optics, and we're going to see it holds true in acoustics too, it's just a wave thing. In fact, it can be demonstrated for the pure wave equation, and we're demonstrating it here for the short wavelength limit. So we have N1 and N2, am I using capitals or not? We have N1 and N2. By the way, defined as some constant frequency divided, so it's just a constant, divided by the speed of sound in the medium. Okay, so when the speed of sound is smaller, the N is larger. Okay, so we have that, and then we think of a ray coming in. Here's our X and Y axes. Actually, let's have it come in a little shallower angle. So there's our theta 1. And if N2 is greater, theta 2. We have the angle of incidence, angle of refraction, and then we know N1 sine theta 1 equals N2 sine theta 2. Okay. And we're trying to prove that using this variational principle, but we then have N of, well, we're now X and Y, and in fact, N is a function of Y, so what we have is N of Y, and then our dl is root 1 plus y prime squared dx, I can just write x1 to x2, equals 0, where y prime is equal to dy over dx. So the hint was to use Euler's second form. Okay, so this is f of y and y prime, but not x explicitly, and then we had df dy prime minus f is equal to some constant. C's already been taken, so we're just going to say it's equal to a. Now the thing about n of y in this expression, just leave it as an n of y and do what has to be done. But n of y is a step function actually. Okay? It just takes on two discrete values. But the thing is, this constant is the one and only constant across that step. Okay? So that you don't have two values of a. Sometimes people think you have two values of a. No, you just have one value of a. N of y is a step function. We're not going to have to do any derivatives or anything fancy with it. What we end up doing is solve for y prime, which is dy dx, which is whatever it is. And then because what you're going to have is the either one value of a constant or another, you know, n sub 1 or n sub 2, this expression, which is the slope of that line, is just going to have a different value on one side as opposed to the other, because these expressions contain different value of n. So you just have to have it all in front of you and analyze your picture to then obtain this here. Okay, pure. Label your graph, carefully understand what's going on, and it's just geometry that this will come out. So That's pretty satisfying. You then get Snell's law. You're not going to solve any fancy differential equation. Once you've isolated this thing, since it is the slope of a line, you just have to interpret it properly. And this will pop out. So that's the one method. Okay. Now the next one is really like bringing out the heavy artillery, just to show Snell's law, but we're going to discuss that also. Okay. So this is the first method. Now we want to use the Hamilton-Jacobi formalism. And here, so Hamilton-Jacobi formalism. There are a couple different ways to go, just as we saw with some of our problems. Won't be anything fancy here, we just got to keep track of everything. So yeah, I don't actually have those equations up, so let's go ahead and write them down first of all. We have d squared c, no, not, where'd it be? C dx quantity squared. Hope I didn't write it wrong before, check. Plus deep C dy quantity squared is equal to omega squared over c squared. And if we want, just as before, we can call that capital N if we want, okay? And it's going to be a function of y. So that's what we start with. So this is capital N squared, right? Yeah. Yes, capital N squared of y. Now this doesn't look exactly like the Hamilton-Jacobi equations we've solved, but no problem there. We can, I've done this a couple different ways. Okay. Let a squared be a constant. Okay, let's have some constant here. I can write let's see what the best way here is. Actually, there is no best way, but yes, okay, back up. So our next step right here is we know that there's going to be a cyclic variable. Okay. So we're going to say let C equal C naught x of y minus omega t. That's the first ansatz here. It's actually going to be cx x plus cy of y minus omega t. That is our separation of variables in the Hamilton-Jacobi formalism, and omega is a constant, just like the energy is a constant. Furthermore, x is cyclic. Okay. X is cyclic, so we can write C is equal to alpha x x plus C y minus omega t. So that's going to be what what we called the action before. And we go into the Hamilton-Jacobi equation with this ansatz. I'm going to erase this, we've seen it. So at this stage, we're just following the rules, okay? It's all coming back to you, right? We've got what we're going to call the Hamilton-Jacobi equation. So we're just working through, first of all, omega's constant, so we can factor off that expression there. Then we're going to do the separation of variables, and then we even have a constant here because x is cyclic. So now we take this back into the Hamilton-Jacobi equation, or the Eichenall equation, let me say. So now we have alpha x squared, right, deep C dx, plus deep C dy squared is going to be this n squared of y. Now I added and subtracted something to the equation. Yes. To make it look like our Hamilton-Jacobi equation with just the energy on the right side, so in this case equals a squared. I just added a squared to each side and subtracted n squared of y, because now it looks the way it looked before when we had the potential energy on the left side and the constant on the right. So this is, the a is actually going to drop out when we're all done, but we can do that. And now we have this constant. We can say, okay, let's let this be alpha y squared. Okay. And then we can let this be alpha x squared plus alpha y squared. I think that's as far as I'm going to take it for you guys. There's still a couple of ways to tackle it, but we already have this. You have to get cy of y, which you can get by solving this differential equation. Deep C dy squared plus a squared minus n squared of y is equal to alpha sub y squared, which is another constant, right? And then it's just saying that the left side equals the right side. So you solve this differential equation, then you go back here. Depending on if you want any time dependence or not, there are a couple of ways to tackle it from here on out. Yeah, but you can find those. Do it two ways. It's possible to ignore the time dependence. It's possible to incorporate it. Same point here that we just had with the variational principle. Namely, these constants here, like these alpha x and the alpha y, they are constants across the boundary. Okay. This n of y, of course, is again a step function. So you don't do any fancy integration. It's a trivial integration on both sides. Go ahead and let your solution meet at the origin from the both sides, just as in our picture, right? So we, once again, when you're done, you've got your x and y, and go ahead and let your solutions meet at the origin for the 1 and the 2. Yeah, and you will discover that Snell's law holds as well using this formalism. At which point we really have a good proof of concept. Okay. So that may be enough. So it's possible just to leave omega as a constant, just to leave it off and deal with these two when you finally use your, remember you've got your beta sub I equals deep C alpha sub y. You've got that whole business to deal with. Or you can actually construct an expression here included using alpha x squared plus alpha y squared. Then you have to modify it with a constant to keep the dimensions right. And if you do that, that constant drops out of the problem as well. Okay, I think I've said enough. So this one you'll find no problem at all from what I said. And here you see we've just taken it through the formalism. This is going to be easy, and then you just got to set everything up right and make sure it works. Okay, good. Other than that, have a good break and enjoy this problem here. And we're going to reproduce this chart once more and carry on with some interesting stuff as well. Okay, see you later.